Out there, drifting silently between Mars and Jupiter, hides something that shouldn't exist, an object in the asteroid belt that moves with the precision of a satellite, yet bears no trace of where it came from or why it behaves this way. Picture a cosmic rule breaker, defying everything we think we know about how celestial bodies move. This isn't science fiction. It's a real mystery that has astronomers around the world utterly stumped. What if I told you that nestled among the rocky debris of the asteroid belt, there's an anomaly so strange, it could force us to rethink the very fabric of our solar system? This enigmatic object doesn't just orbit the sun like its neighbors, it dances. Its path is too orderly, too deliberate, almost as if it's being guided by invisible hands. Yet when scientists trace its origins, they hit a dead end. No known asteroid, no leftover fragment from a collision, no rogue piece of planetary debris matches its behavior. It's as if this object appeared out of nowhere, challenging our understanding of gravity, motion, and the history of our cosmic backyard. How can something so out of place exist without explanation? That's the question haunting researchers right now. Today, we're diving deep into this celestial detective story, unraveling the clues behind the asteroid belt's most baffling resident. We'll explore the leading theories. Could it be a captured alien satellite, a relic from a long-lost civilization, or something even more extraordinary? And why does this one strange rock hold the potential to rewrite the textbooks? Strap in, because this isn't just a tale of space oddities. It's a front-row seat to a mystery that blurs the line between the possible and the unimaginable. By the end of this journey, you might never look at the night sky the same way again. The year 2016 marked a turning point in our understanding of the asteroid belt, not because of what was expected, but because of what defied all expectations. During routine observations, telescopes trained on the space between Mars and Jupiter locked onto an object that immediately stood out. Instead of following the chaotic, elliptical paths of its rocky neighbors, this lone wanderer traced a smooth, almost calculated orbit, more like a satellite circling a planet than a random chunk of cosmic debris. At first, astronomers wondered if it might be a piece of human-made space junk, perhaps a forgotten probe or a discarded rocket stage drifting far from home. But the math didn't add up. Its trajectory was all wrong for anything launched from Earth, and spectroscopic analysis revealed a composition unlike any known spacecraft material. What made this discovery even more unsettling was the absence of any plausible explanation. Natural satellites' moons are tethered to planets by gravity, yet this object orbited the Sun independently, mimicking the precision of something artificial without any visible parent body. The scientific community scrambled to make sense of it. Could it be a fragment from a long-ago collision, hurled into this bizarre path by some cosmic fluke? Or was there something far stranger at play? Theories flew, but hard evidence remained elusive. Even the most advanced simulations couldn't recreate its orbit without introducing hypothetical forces or unseen influences. The implications were profound. If this wasn't space debris and it wasn't a natural satellite, what was it? The mystery deepened when researchers realized its surface reflected light in a way that didn't match typical asteroids or comets. Some speculated about exotic origins. Could it be a relic from another star system, a captured fragment from a distant planetary system? Others dared to ask the question no one wanted to voice aloud. Were we looking at something that wasn't entirely natural? The debate raged, but one thing became clear. This wasn't just another rock in the belt. It was a cosmic outlier, challenging the very frameworks we use to understand our solar system. And with every new observation, the puzzle only grew more complex. Orbital mechanics should be predictable, a cosmic ballet governed by gravity's unbreakable rules. Yet this object dances to its own rhythm, tracing a path that leaves astronomers scratching their heads. While typical asteroids follow stretched, oval-shaped orbits around the Sun, this rebel glides with unnatural smoothness, as if tugged by forces we can't yet see. The math reveals something even stranger. Its movement suggests the gravitational whisper of a nearby mass, like a hidden puppeteer guiding its motions. But here's the twist: when telescopes scan the area, they find nothing. No rogue planet, no stealth black hole, not even a dense cluster of dark matter. Just empty space where physics insists something ought to be. This cosmic contradiction has sparked wild debates in observatories worldwide. One camp argues we're looking at an interstellar hitchhiker, a rare visitor from another star system, flung into our asteroid belt during a close encounter millennia ago. These wanderers do exist. Remember Oumuamua, that cigar-shaped oddity that zipped through our solar system in 2017. But unlike temporary guests, this object seems settled, integrated into our celestial neighborhood while stubbornly keeping its outsiders' quirks. Then there's the moon theory. Imagine a scenario where Jupiter or Mars once had an extra moon that shattered during some ancient collision. A surviving fragment could theoretically be nudged into this bizarre orbit, carrying the ghostly signature of its former parent planet's gravity. It's a poetic idea, a celestial orphan still moving as if tethered to a world that no longer holds it. Yet with every new observation, the mystery deepens. Last year, radar imaging revealed the object spins unusually fast for its size, completing a rotation every 2 hours, another anomaly that defies textbook expectations. Some researchers whisper about exotic possibilities. Maybe it's hollow or contains materials that alter its gravitational interactions. Others cautiously suggest we might need to reconsider our models of orbital dynamics altogether. The truth is, we're watching science in real time, a living puzzle that resists easy answers. Every attempted explanation raises 3 new questions, and that's what makes this so thrilling. Whether it's a cosmic accident or something more deliberate, one thing's certain: this celestial maverick is teaching us how much we still have to learn about the silent symphony of our solar system. Theories abound about this cosmic enigma, each more fascinating than the last. Let's start with the most grounded explanation: the planetary collision hypothesis. Picture the early solar system, a chaotic shooting gallery of protoplanets smashing together in violent mergers. Some astronomers suggest our mystery object could be a surviving fragment from one of these ancient crashes, a planetary shard flung into this peculiar orbit by forces we can barely imagine. There's precedent for this. The asteroid Pallas, one of the belt's largest residents, shows scars hinting at a catastrophic impact in its past. But here's the catch: no known collision could account for both this object's composition and its eerily smooth trajectory. It's like finding a perfectly polished diamond in a quarry of rough stones. Then there's the co-orbital theory, which paints an even more intriguing picture. Some asteroids share stable orbits with larger bodies, locked in gravitational resonance. Think of 2 dancers spinning around each other without ever touching. Jupiter's Trojan asteroids are prime examples, trailing and leading the gas giant in its path around the Sun. Could our mystery object be performing a similar dance with an invisible partner? The math suggests it's possible, but here's the problem: telescopes can't find anything substantial enough to explain its movements. It's as if it's waltzing with a ghost, responding to gravitational tugs from empty space. Now we come to the most controversial idea: the possibility, however remote, that this isn't a natural object at all. Before you dismiss this as science fiction, consider this. Humanity has already accidentally created artificial asteroids. In 2007, a spent rocket booster temporarily entered solar orbit, masquerading as a near-Earth asteroid until astronomers recognized its true nature. Could our mystery object be something similar, but not of human origin? The lack of reflective surfaces or metallic signatures makes this unlikely, yet the notion lingers because it would explain the object's uncanny orbital precision. What's truly remarkable is how each theory unravels upon closer inspection. The collision fragment can't account for the orbit. The co-orbital idea lacks a visible partner. The artificial construct theory has no physical evidence. It's as if the universe handed scientists a riddle wrapped in a paradox. Every solution only deepens the puzzle. And that's precisely why this object matters. Whether it's a cosmic fossil, a gravitational anomaly, or something beyond our current understanding, its very existence pushes us to question what we think we know about the asteroid belt's history. One thing's certain, this isn't just academic curiosity. Unraveling this mystery could rewrite chapters in our solar system's story, revealing hidden forces or forgotten collisions that shaped the space around us. Every new observation peels back another layer, showing us how much we still have to learn about the silent, swirling dance of rocks between Mars and Jupiter. Now we arrive at the most tantalizing and controversial explanation for our cosmic oddity. The possibility that this object isn't natural at all. Imagine stumbling upon a perfectly carved stone in the wilderness with no signs of human tools nearby. That's the level of bewilderment scientists face when studying this asteroid belt anomaly. Its movements are so precise, so deliberate, that some researchers can't shake the feeling we might be looking at something engineered. The idea of an artificial origin isn't new. It's a thread woven through decades of space exploration. Remember the infamous WOW signal of 1977, a radio burst so unusual it sparked theories of extraterrestrial contact. Or the more recent Oumuamua debate, where Harvard astronomers suggested it might be an alien light sail. This object reignites those same questions. Its orbit resembles a satellite, not the chaotic tumbling of a typical asteroid, but the controlled glide of something designed to maintain position. Mainstream science, of course, remains skeptical. Extraordinary claims require extraordinary evidence, and so far, there's no smoking gun, no unusual radio emissions, no metallic sheen, no telltale signs of technology. Spectroscopic analysis shows a surface composition not wildly different from other asteroids, though some argue advanced alien tech might deliberately mimic natural materials. Critics point out that nature itself is full of oddities. Take the hexagonal storm on Saturn or the bizarre rectangular icebergs of Antarctica that defy intuition without being artificial. Yet the theory persists, fueled by gaps in our understanding. Why? Because humanity has already accidentally created false asteroids. In 2002, astronomers temporarily catalogued an object labeled JO202e as a near-Earth asteroid until they realized it was a discarded Saturn V rocket booster from the Apollo 12 mission, adrift in space for decades. If we can mistake our own debris for celestial bodies, could the reverse be true? Might something built by another civilization now hide in plain sight among the rubble of the asteroid belt? Science fiction has long played with this concept, from Arthur C. Clarke's Monolith in 2001 to the derelict ships of Alien, but reality often outpaces imagination. Consider the ongoing search for technosignatures, unusual patterns in light, heat, or radio waves that could hint at intelligent design. Projects like Breakthrough Listen scan the cosmos for such clues, though nothing conclusive has emerged from this object yet. The truth is, we may never know without closer inspection. Imagine sending a probe to study it up close, to scrape its surface or map its interior. The data could reveal whether its structure holds unnatural symmetries or materials arranged in ways physics wouldn't predict. Until then, the artificial origin hypothesis remains in limbo, a captivating what if that challenges us to keep looking, questioning, and wondering what else might be hiding in the shadows of our solar system. Perhaps the most profound lesson here isn't about aliens at all, but about human curiosity. This object, whatever it is, forces us to confront the limits of our knowledge. Whether it's a relic of some ancient collision, a gravitational anomaly, or something beyond our current imagination, its mystery reminds us that the universe still holds surprises, and that's what makes exploration so thrilling. Most astronomers don't reach for alien megastructures or interstellar artifacts. When faced with cosmic mysteries, they look to the universe's own playbook. And in this case, the leading theories point to natural, albeit extraordinary, origins. Take the Trojan asteroid hypothesis. These celestial bodies are cosmic hitchhikers, locked in gravitational harmony with planets, typically sharing their orbit around the Sun. Jupiter alone has thousands of these Trojan companions, clustered in swarms at stable points ahead of and behind the gas giant. But here's where our mystery object throws a wrench in the works. It's not parked in one of these predictable zones. Instead, it's executing a solo performance in the asteroid belt, mimicking the stability of a Trojan without the gravitational anchor of a planetary partner. That's like finding a synchronized swimmer performing alone in the middle of the ocean. No team, no choreographer, just flawless precision defying the odds. Then there's the disrupted protoplanet theory, which paints a dramatic picture of the solar system's violent youth. Billions of years ago, this region wasn't just a belt of rubble. It was a construction zone where embryonic planets collided, merged, and sometimes shattered. Some researchers suggest our enigmatic object could be a surviving core fragment of one of these failed worlds, a planetary fossil preserving clues to a cataclysm lost to time. The asteroid Vesta offers a tantalizing parallel. Scans reveal it has a layered structure, almost like a miniature planet stripped of its outer shell. But our mystery target lacks Vesta's telltale geological scars, and its orbit is far more refined than the chaotic paths typical of collision debris. What makes these natural explanations so compelling and so frustrating is how close they come to fitting, only to fall just short. Supercomputer simulations can recreate Trojan-like orbits, but only by tweaking variables like unseen gravitational nudges or hypothetical past encounters. Telescopes like the Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile are scanning for faint heat signatures or chemical traces that might hint at the object's history, but every dataset adds new wrinkles. Last year, a team at the European Southern Observatory reported an unusual concentration of rare metals in its spectral analysis, not enough to scream artificial, but enough to raise eyebrows. The real challenge lies in the gap between what we know and what we're seeing. Nature is full of outliers, rogue planets drifting between stars, hypervelocity stars ejected from galaxies, even entire black holes wandering unseen. But those phenomena, however extreme, still operate within the rules of physics. This object dances along the edge of those rules, close enough to be plausible yet just beyond our grasp. That's why the scientific community isn't settling for easy answers. From Japan's Subaru telescope to NASA's upcoming Nancy Grace Roman Space Telescope, observatories worldwide are turning their lenses toward this cosmic conundrum, not just to solve a puzzle, but to test whether our models of solar system evolution need rewriting. Perhaps the most humbling thought, however exotic the explanation turns out to be, the universe has likely crafted stranger things we haven't even dreamed of yet. Whether it's a gravitational fluke, a relic of planetary chaos, or something entirely new, this object is a reminder that the asteroid belt isn't just a junkyard of the past, it's a frontier where the next great discovery might be hiding in plain sight. To understand just how bizarre this object truly is, let's stack it against the asteroid belt's usual suspects. Most residents here are cosmic nomads, jagged fragments left over from the solar system's construction, tumbling along chaotic paths shaped by billions of years of gravitational nudges. Their orbits are like fingerprints, no two exactly alike, each telling a story of collisions, near misses, and the slow dance of celestial mechanics. But our mystery object, it moves with the eerie precision of a moon, tracing a path so steady it almost feels choreographed. And that's the problem. Moons don't exist without planets, yet scans show nothing massive enough nearby to explain its behavior. It's like watching a compass needle point steadfastly north in a room with no magnetic field. This isn't the first time we've encountered cosmic oddballs, of course. The interstellar visitor Oumuamua made headlines in 2017 for its peculiar acceleration and elongated shape, traits so unusual they sparked debates about natural versus artificial origins. But there's a critical difference. Oumuamua was just passing through, a tourist streaking through our solar system at breakneck speed. Our asteroid belt enigma, by contrast, has taken up residence. It's not a visitor, it's a local one that somehow brought its own rulebook. Then there's the question of composition. Early spectroscopic data suggests a mix of silicates and metals, not unlike many common asteroids. But dig deeper and anomalies emerge. Last year, a team using the Gemini Observatory in Hawaii detected unexpected spikes in infrared readings, hints of minerals that typically form under extreme pressures, like those found deep inside planetary cores. Could this be a shattered piece of a protoplanet's heart, flung into the belt during some ancient catastrophe? It's a compelling idea, except for one gaping hole. No known collision event explains how such a fragment could end up in this specific, satellite-like orbit. The more we compare this object to known celestial bodies, the more it defies categorization. Trojans share orbits with planets this doesn't. Captured moons show signs of tidal heating, this hasn't. Interstellar objects race through on hyperbolic trajectories, this lingers. Even the bizarre, active asteroids that sporadically sprout comet-like tails don't match its profile. It's as if the universe assembled this object from spare parts left out of the instruction manual. Perhaps the most tantalizing clue lies in what's missing. Every theory that fits one piece of the puzzle, its orbit, its spin, its composition falls apart when applied to the others. Like a detective staring at a suspect who's simultaneously too tall, too short, and the perfect height, astronomers are left questioning whether they're dealing with one anomaly or several layered atop each other. One thing's certain, this isn't just another space rock. It's a mirror held up to our assumptions, revealing how much we still don't know about the seemingly familiar asteroid belt. And that's what makes it irresistible, not just for scientists, but for anyone who's ever looked up at the night sky and wondered what other secrets might be hiding in the darkness. Telescopes from Chile's Atacama Desert to Hawaii's Mauna Kea have turned their gaze toward this celestial rebel, gathering clues like detectives at a cosmic crime scene. Early measurements reveal an object roughly 1 kilometer wide, small enough to be overlooked, yet large enough to behave unlike anything else in the belt. Its surface, when analyzed through spectrographs, shows the familiar fingerprints of silicates and metals, much like ordinary asteroids. But the moment scientists dig deeper, the similarities crumble. The way light bounces off its surface, its albedo doesn't align with any known asteroid family. Most reflect sunlight in predictable patterns, but this one scatters it oddly, as if its exterior is layered with some exotic material or pocked with unnatural textures. Then there's the puzzle of density. By tracking its gravitational influence on nearby objects and calculating its mass, researchers expected numbers typical of loosely packed rubble piles common among asteroids. Instead, the data suggests something far more compact, as if this object is either unusually solid or harbors hollow spaces within. Neither scenario fits the standard models. If it's dense, why hasn't it shattered under collisions like its neighbors? If it's porous, why doesn't it tumble chaotically like other rubble pile asteroids? The contradictions pile up. Perhaps the most telling observation is what's missing: the faint glow of a coma or the streaking tail of a comet. This rules out icy origins, confirming it's not a dormant comet warming as it nears the sun. Yet its rotation adds another layer of intrigue, spinning once every 2 hours, faster than most objects its size. Such rapid spins typically fling loose material into space, yet no debris field surrounds it. It's as if this thing is held together by some unseen force, defying the centrifugal chaos that should tear it apart. Every new dataset deepens the enigma. Submillimeter wave scans from the ALMA array in Chile hint at thermal anomalies, patches that heat and cool out of sync with the rest of the surface, almost as if its interior conducts heat unevenly. Meanwhile, radar imaging from Arecibo before its collapse revealed a bizarrely smooth reflection pattern, unlike the jagged echoes most asteroids produce. Some researchers whisper about metallic inclusions or even crystalline structures beneath the surface, though no one's ready to stake their reputation on such speculative claims. What's fascinating isn't just the anomalies, but how they refuse to form a coherent picture, like assembling a jigsaw puzzle where every piece seems from a different box. The data teases without revealing. Is this a fragment of a shattered protoplanet's core, a captured interstellar oddity, or something else entirely? The telescopes keep watching, but for now, the asteroid belt's most mysterious resident guards its secrets tightly, challenging us to rethink not just what we see, but how we see it. The universe, it seems, still has a few tricks up its sleeve. Gravity, the invisible architect of our solar system, usually follows predictable rules until it doesn't. This enigmatic object's orbit behaves as if tugged by something massive lurking nearby, yet every scan of its surroundings comes up empty. It's like feeling the breeze from an open window but finding no window at all. The math insists there should be a gravitational partner, perhaps a hidden dwarf planet or a dense knot of dark matter, but telescopes see only void. This contradiction has astronomers revisiting decades of assumptions about what might be hiding in the asteroid belt's shadows. One compelling theory points to rogue dwarf planets, remnants of the solar system's chaotic infancy that never grew into full-fledged worlds. These stealthy giants could drift undetected, their faint heat signatures lost in the vastness of space. In 2021, simulations from the University of Arizona suggested hundreds of Mars-sized objects might have once roamed the early solar system, most ejected into interstellar space. But what if a handful stayed behind, lurking just beyond our sight? The gravitational fingerprints of such an object could explain our mystery target's peculiar path without requiring exotic physics. Then there's the dark matter hypothesis, a far more radical idea. Most dark matter is thought to float in diffuse halos around galaxies, but some models allow for dense clumps drifting like invisible icebergs. If one such clump crossed paths with our object, its gravity might subtly steer the rock's orbit without leaving a trace. It's a long shot. Dark matter interacts so weakly with normal matter that detecting even a massive concentration is nearly impossible with current technology. Yet the mere possibility has theorists dusting off papers on alternative gravity models, wondering if this anomaly could be the thread that unravels a much larger cosmic mystery. The stakes are higher than they seem. Confirming an unseen mass in the asteroid belt wouldn't just solve this puzzle, it would rewrite the rules of celestial navigation. Space agencies rely on precise gravity maps to plot spacecraft trajectories. An unaccounted-for dwarf planet or dark matter pocket could send probes wildly off course. Even more tantalizing is what these findings might reveal about the belt's formation. Current models paint it as a quiet graveyard of failed planets, but if hidden giants or exotic matter stir its depths, we may be looking at a far more dynamic and dangerous region than anyone suspected. For now, the truth remains just out of reach, dancing at the edge of our instrument's sensitivity. Upcoming missions like the Vera Rubin Observatory's 10-year sky survey promise unprecedented scrutiny of the belt's dark corners. Whether they'll find a missing planet, an invisible force, or something entirely unforeseen, one thing's certain: this object has already done its job. It's pulled back the curtain on how much we still don't understand about the silent, swirling expanse between Mars and Jupiter, and the hidden forces that might be shaping it from the shadows. The asteroid belt has always been a cosmic cabinet of curiosities, each object telling its own fragment of the solar system's history. Take Ceres, the belt's largest resident, a dwarf planet with icy volcanoes and a subsurface ocean that blurs the line between asteroid and world. Or Vesta, whose reflective surface still bears scars from a colossal impact that sent fragments raining down on Earth as meteorites. These are the celebrities of the belt, well studied and understood. But our mystery object, it's the uninvited guest at the party, the one that doesn't fit the dress code. This isn't the first time astronomers have been blindsided by celestial oddballs. History is littered with moments when the universe forced us to rewrite the textbooks. Consider Pluto's demotion in 2006, not just because it was small, but because the Kuiper belt revealed a crowd of icy worlds just like it. Or the shocking discovery of Oumuamua, the first known interstellar visitor, which barreled through our solar system with a shape and speed no one predicted. These anomalies didn't just challenge our knowledge, they expanded it, proving that the cosmos loves to subvert expectations. What makes this object different is its refusal to conform to any existing category. Ceres and Vesta, for all their quirks, still obey the rules of orbital mechanics. Even Pluto's eccentric path makes sense once you account for Neptune's gravitational nudges. But our enigma, it's like a clock that ticks perfectly yet has no visible gears. Its very existence forces us to confront a humbling truth. The asteroid belt, a region we've mapped and studied for centuries, might still hold secrets we've barely begun to glimpse. The parallels to past discoveries are striking. When Uranus was found in 1781, it was the first planet discovered with a telescope, appending the ancient model of a six-planet solar system. Later, discrepancies in Uranus's orbit led to the prediction and eventual discovery of Neptune, proving that anomalies can be signposts to hidden truths. Could this object be a similar clue, pointing to something we've overlooked? A missing planetoid, perhaps, or a gravitational ripple from the solar system's violent youth? One thing's certain, every astronomical revolution begins with an outlier. Galileo's telescopes revealed moons orbiting Jupiter, shattering the Earth-centered universe. The asteroid belt itself was once just a mathematical hypothesis, the missing planet between Mars and Jupiter, until Ceres proved it was a realm of fragments, not a single world. Now, as then, the universe is handing us a puzzle wrapped in mystery. Whether this object is a relic of chaos, a gravitational glitch, or something stranger, its greatest gift may be the questions it forces us to ask. After all, it's not the objects that fit our models that push science forward. It's the ones that break them. There's something about a cosmic mystery that unites us amateur stargazers pointing backyard telescopes toward the belt, Reddit threads dissecting every new finding, even late-night podcasts spinning wild tales about alien artifacts. This object hasn't just puzzled scientists, it's become a cultural phenomenon, a Rorschach test for our collective imagination. Scroll through space forums, and you'll find threads with thousands of replies, each theory more creative than the last. Some argue it's a relic from an ancient civilization, a monument left behind by travelers who passed through our solar system eons ago. Others propose it's a natural oddity, a cosmic glitch that reveals hidden laws of physics. The chatter isn't confined to niche corners of the internet either. Major documentaries have dedicated segments to it, their narrators dropping ominous hints about the one object that shouldn't exist. Even Hollywood's taken notice screenwriters quietly filing away ideas for the next big sci-fi thriller. What's fascinating isn't just the speculation, but why this particular object resonates so deeply. Space is full of anomalies, yet few capture the public's attention like this one. Maybe it's the simplicity of the mystery. Here's a rock that moves wrong, and no one can say why. No black holes, no warp drives, just a quiet defiance of expectations that feels almost personal. It taps into that childlike wonder of looking up at the night sky and realizing the universe still holds secrets. You don't need a PhD to grasp the thrill of that. The enthusiasm isn't just passive either. Citizen scientists have mobilized, combing through archival telescope data for overlooked clues. Online collaboratives like Zooniverse have launched projects to track its movements, crowdsourcing observations from amateurs worldwide. In 2023, a high school astronomy club in Norway even helped pinpoint an irregularity in its rotation, a discovery that later made it into a peer-reviewed paper. This isn't just science, it's a shared adventure, proof that the most tantalizing mysteries don't belong to experts alone. Yet beneath the excitement lies a deeper truth. Humanity's obsession with the unknown hasn't faded. From Stone Age star charts to modern exoplanet hunts, we've always been drawn to the edges of understanding. This object, whatever it is, has become a mirror reflecting our timeless craving to explore, to question, to push beyond the map's edge. And that's why it matters, not just for the answers it might one day reveal, but for the questions it keeps alive in all of us. NASA doesn't throw resources at cosmic curiosities without good reason. So when both Hubble and the James Webb Space Telescope pivoted toward this asteroid belt anomaly, the scientific world took notice. These aren't just any instruments, they're humanity's most powerful eyes on the universe, capable of spotting the faintest heat signatures and analyzing light spectra from billions of kilometers away. Early data from Hubble's ultraviolet sensors revealed something odd. The object's surface reflects UV light differently than typical asteroids, almost as if its outer layer has been altered by processes we don't yet understand. Meanwhile, James Webb's infrared gaze is hunting for molecular fingerprints, organic compounds, water signatures, or even unexpected metals that could hint at its origins. The fact that both telescopes are involved tells you this isn't just another space rock. It's a priority, but NASA's interest goes beyond observation. The agency's Lucy mission, currently en route to Jupiter's Trojan asteroids, carries instruments that could indirectly shed light on our mystery. Though Lucy won't pass near this object, its study of primitive asteroids may reveal whether our enigma shares traits with these ancient building blocks of the solar system. Then there's Psyche, the upcoming probe destined for a metal-rich asteroid of the same name. While its target is different, The mission's suite of spectrometers and magnetometers could help scientists understand how metallic objects behave in space, knowledge that might explain our target's unusual density and reflectivity. The real question isn't whether NASA will send a dedicated mission, it's when. Behind closed doors, researchers are already drafting proposals for a flyby or even a sample return expedition. Imagine a spacecraft swooping in to photograph this object up close, measuring its gravitational field, or even snatching a handful of its surface material. The data could settle debates overnight. Is it a captured interstellar visitor, a shattered protoplanet core, or something even more extraordinary? Until then, scientists are piecing together clues like a cosmic jigsaw, knowing full well that this might be one of those rare puzzles that changes how we see our place in the universe. What makes NASA's involvement so pivotal isn't just the technology, it's the collaboration. Findings from Hubble and Webb are being cross-referenced with ground-based observatories in Chile, Japan, and the Canary Islands, creating a global network of scrutiny. Every new image, every spectral line adds another piece to the story, and that's the beauty of this mystery. It's not just about one strange object. It's about what that object reveals about the asteroid belt's hidden complexities, and whether we're finally ready to acknowledge how much we still have to learn. When a cosmic mystery transcends borders, so does the quest to solve it. Across continents, astronomers from the European Space Agency, Japan's JAXA, and observatories from Chile to South Africa have locked onto this celestial rebel, pooling telescopes, supercomputers, and decades of collective expertise. It's a scientific relay race where each team passes data to the next as the object swings into their field of view, because no single nation can track it alone. The challenge: this thing doesn't follow a predictable schedule. While most asteroids move like clockwork, our Enigma zigzags just enough to slip through observation gaps, forcing researchers into a high-stakes game of celestial hide and seek. The beauty of this collaboration lies in its urgency. When JAXA's Subaru telescope in Hawaii catches an odd thermal signature, the alert pings to ESA's Near-Earth Object Coordination Center in Italy within hours. Chinese astronomers using the 500-meter aperture spherical telescope FAST then scan for radio anomalies, while American teams at the Arecibo Successor facility in Puerto Rico double-check the radar echoes. This isn't just about sharing notes, it's about stitching together a 24/7 surveillance net across Earth's rotation. But synchronization is harder than it sounds. Time zones, language barriers, and even competing academic priorities can slow the flow. Imagine a dozen detectives working the same case, each with their own methods, but all chasing a suspect that vanishes at random. What's remarkable is how these hurdles are being overcome. The International Astronomical Union has fast-tracked a special task force, while open-source platforms let citizen scientists contribute sightings. Last year, an amateur astronomer in Namibia spotted a sudden brightness spike in the object, a clue professionals might have missed during their scheduled observing windows. That data point later helped explain its erratic spin, proving crowdsourcing isn't just helpful, it's transformative. Yet the real lesson here isn't technical, it's philosophical. In an era of terrestrial divisions, this object has become a silent diplomat, reminding us that the universe doesn't care about borders or politics. Whether it's a fragment of planetary chaos or something stranger, unraveling its secrets demands something rare on Earth: unity. And that may be its most profound gift, not just the answers it offers about space, but the example it sets for how we explore them together. The Vera Rubin Observatory, perched atop Chile's Cerro Pachón, is about to revolutionize our hunt for cosmic oddities, and this asteroid belt enigma is at the top of its watch list. Slated to begin its 10-year legacy survey of space and time in 2025, Rubin's 8.4-meter mirror and massive 3.2 gigapixel camera will scan the entire southern sky every few nights, capturing changes too subtle for most telescopes to notice. For our mystery object, that means something groundbreaking: continuous monitoring. No more gaps in observation, no more guessing about its movements between sightings. Rubin could catch subtle orbital shifts, unexpected outgassing, or even faint companions hidden in its glare, clues that might finally crack this case wide open. But Rubin's just the opening act. Next-generation spectrographs like those on the extremely large telescope, currently under construction in Chile's Atacama Desert, will dissect the object's light with unprecedented precision. Imagine being able to read its surface chemistry like a barcode, not just spotting silicates or metals, but detecting trace elements that could reveal its birthplace. Did it form in the scorching inner solar system or the icy fringes? Was it forged in a violent collision or gently nudged into place by gravitational tides? These are the fingerprints spectroscopy could uncover. Then there's radar, the tool that turned asteroid Bennu from a blurry dot into a detailed map ahead of NASA OSIRIS-REx mission. Facilities like the Green Bank Telescope in West Virginia and the upcoming next-generation Arecibo could bounce radio waves off our target, revealing its shape, rotation axis, and even surface texture. A jagged, irregular form would suggest a collision fragment, while unnaturally smooth features might hint at erosion from eons in deep space, or something more provocative. The Holy Grail, though, remains a sample return mission. Picture a spacecraft like Japan's Hayabusa 2, which brought back grains from asteroid Ryugu, but designed specifically for this object. A robotic arm could scrape its surface, scooping up materials sealed away from Earth's contaminating atmosphere. Lab analysis might uncover isotopic ratios found nowhere in our solar system, proof of interstellar origins, or exotic minerals shaped by conditions we've never replicated. Of course, cosmic detective work moves at the speed of funding cycles and rocket launches. Answers won't come overnight, but every tool in the pipeline, from Rubin's relentless gaze to the prospect of touching this object firsthand, brings us closer to solving a puzzle that's already rewritten the rules of what we thought possible. The real thrill, however this story ends, the journey there will remind us why we explore, not just for answers, but for the joy of finding questions we hadn't even dreamed to ask. Studying this cosmic rebel isn't like examining the moon or Mars. It's more like trying to read a license plate on a speeding car from halfway across a foggy city. At roughly 1 kilometer wide and drifting millions of kilometers away, the object occupies a frustrating middle ground, too small for most telescopes to resolve details, yet just large enough to tease us with glimpses of its oddities. Even Hubble, with its legendary optics, sees it as little more than a pixelated dot. The challenge: every scrap of data, every spectral line, every flicker of reflected light, has to be wrung from that single pixel, like deciphering an entire novel from a single smudged word. Then there's Earth's own atmosphere, nature's ultimate prankster for astronomers. Turbulent air currents distort light, turning crisp observations into blurry mirages. Adaptive optics help, using laser guide stars to correct distortions in real time, but they're not perfect. Imagine squinting through a snowstorm while someone shakes your shoulders. That's what it's like for telescopes fighting atmospheric interference. Chile's high-altitude observatories mitigate this with dry, thin air, but even there, the object's faintness means exposures often require hours of painstaking tracking, with researchers praying clouds don't roll in mid-session. Competition for telescope time adds another layer of frustration. The world's premier observatories operate like elite nightclubs, with scientists submitting proposals months in advance for coveted slots. Your project might lose out to a supernova hunt or exoplanet survey, leaving your team stuck waiting while the object drifts on, its secrets intact. Some researchers have resorted to guerrilla astronomy, piggybacking on unrelated observations or scraping data from archival scans, hoping to spot overlooked clues in someone else's homework. Yet the most maddening hurdle might be the asteroid belt itself. This region isn't some orderly celestial highway, it's a demolition derby of rocks, each jostling the others with gravitational nudges. Pinpointing the object's exact path requires accounting for countless tiny perturbations, like predicting a marble's roll through an earthquake. Even then, uncertainties linger. Last year, a team at Caltech had to scrap weeks of planned observations when the object veered slightly off its predicted course, likely nudged by some unseen neighbor. Despite these obstacles, scientists aren't backing down. They're getting creative. Citizen science initiatives like A Backyard Worlds enlist amateur astronomers to scour telescope data, their fresh eyes catching anomalies professionals might miss. Machine learning algorithms now sift through decades of images, flagging subtle changes in the object's brightness or position that could hint at surface features or rotation quirks. And when all else fails, there's sheer persistence, like the Japanese team that camped out at the Subaru telescope for 3 straight nights, surviving on instant noodles until they finally bagged the high-resolution spectra they needed. What keeps them going? The tantalizing possibility that this one stubborn pixel might hold the key to something monumental. Whether it's a fragment of a lost world, a gravitational anomaly, or something even wilder, the reward isn't just solving a puzzle, it's rewriting the rules. And that's worth every foggy night, every rejected proposal, every cup of cold coffee. Because in the end, the universe's greatest mysteries don't surrender easily. They make us work for them. Every great leap in astronomy begins with a single anomaly, a stubborn piece of data that refuses to fit the mold. This enigmatic object in the asteroid belt isn't just a curiosity. It's a key that could unlock entirely new chapters in our understanding of the cosmos. Take Pluto's reclassification as a dwarf planet. What seemed like a demotion actually revealed a vibrant new category of icy worlds in the Kuiper belt. Similarly, cracking the code of this celestial rebel might force us to redraw the boundaries between asteroids, moons, and something entirely new. Imagine discovering that the asteroid belt harbors a previously invisible class of objects' bodies that behave like satellites but exist independently, challenging the very definitions we've relied on for centuries. The implications ripple far beyond labels. Orbital mechanics, the clockwork rules governing celestial motion, are the backbone of space exploration. Missions like a Lucy probe rely on precise calculations to navigate the asteroid belt's gravitational currents. But if this object's movements hint at unseen forces, whether hidden masses, exotic matter, or gaps in our equations, every trajectory calculation, every mission plan might need revisiting. It's like discovering ocean currents after centuries of sailing blind. Suddenly, the maps we trusted have uncharted depths. Then there's the tantalizing possibility of planetary archaeology. The asteroid belt is already a graveyard of failed worlds, fragments of protoplanets shattered in the solar system's violent youth. If this object is a surviving core fragment or a piece of a lost super-Earth, its composition could reveal secrets about planetary formation that no intact planet ever could. Think of it as finding a fossilized dinosaur heart. While bones tell us about structure, preserved soft tissue reveals how life actually functioned. But the most exciting prospect. This mystery might be a signpost pointing to phenomena we've never considered. When Neptune's orbit didn't match predictions, mathematicians didn't just tweak the numbers, they predicted an eighth planet's existence. Today, we're staring at another gravitational whisper, one that could hint at anything from rogue dwarf planets to flaws in Einstein's relativity at cosmic scales. Every time astronomy confronts the inexplicable, the reward isn't just an answer, it's a whole new set of questions, reshaping our place in the universe. The clock is already ticking. Next-generation telescopes and AI-driven data analysis are turning the sky into a living laboratory, where anomalies like this don't linger in obscurity for long. Whether it's a natural oddity or something more extraordinary, one thing's certain: the moment we solve this puzzle, the solar system will feel both more familiar and infinitely stranger than we ever imagined. In the swirling vortex of speculation surrounding this cosmic oddity, one thing becomes crystal clear: science thrives on evidence, not just excitement. While online forums buzz with theories about alien artifacts or hidden civilizations, the reality is far more nuanced. Respected astronomers like Dr. Amy Mainzer at NASA Jet Propulsion Laboratory remind us that extraordinary claims require extraordinary proof. And so far, no smoking gun, no bizarre radio signals, no unnatural surface patterns has emerged to suggest anything beyond natural phenomena. That doesn't make the object any less fascinating. It simply grounds the mystery in the rigorous process of discovery. Take the hollow asteroid theory, for instance. Some argue its unusual density readings hint at an artificial structure, but planetary scientists point to pumice like volcanic rocks in space, natural formations full of voids. Similarly, the idea of a captured interstellar object gains traction until you consider how unlikely it is for something from another star system to settle into such a stable orbit. Statistically, most interstellar visitors should be fleeting, like Oumuamua, not permanent residents of our asteroid belt. The scientific method's beauty lies in its patience. While pop culture races to sensationalize, researchers methodically eliminate possibilities. Spectroscopic analysis rules out certain materials. Orbital simulations test gravitational scenarios. Thermal maps compare it to known asteroids. Each step narrows the field, even if answers remain elusive. This deliberate pace isn't lack of curiosity, it's respect for the truth. After all, history is littered with cosmic mysteries that turned out to be mundane. Martian canals that were optical illusions, alien radio signals that were pulsars, even a supposed UFO that was just Venus shining unusually bright. Yet dismissing wild theories outright would be a mistake. Sometimes the craziest ideas, like continental drift or quantum entanglement, were once ridiculed before evidence mounted. The key difference: those ideas made testable predictions. If someone claims this object is artificial, what measurable trait would confirm it? Metallic alloys not found in nature. Geometric surface features. Until such evidence appears, the scientific consensus leans toward natural explanations, however unconventional. This balancing act between open-mindedness and skepticism is how real breakthroughs happen. Whether the object ultimately reveals itself as a gravitational fluke, a planetary fossil, or something entirely new, the process of debunking myths ensures we don't miss the forest for the trees. Because in the end, the universe's truths are often stranger than fiction, but they always leave fingerprints, and those fingerprints are what science lives to trace. This cosmic oddity isn't just a puzzle for seasoned astronomers, it's a golden opportunity for students diving into the wonders of space science. Picture a classroom where textbooks come alive, where equations on a page suddenly connect to a real-world mystery unfolding millions of kilometers away. That's the power of this object. It turns abstract concepts like orbital mechanics into something tangible, even thrilling. Teachers can point to its bizarre path and say, "This is why we study gravity. This is why math matters." It's one thing to calculate elliptical orbits on paper, but watching an actual celestial body defy those calculations, that's the kind of spark that ignites lifelong curiosity. The beauty lies in its contradictions. Most asteroids fit neatly into categories: C-types, S-types, M-types based on composition and orbit, but this outlier. It's a living lesson in why science never stops questioning. Students learn early that classification systems are tools, not absolute truths, and here's the proof: an object that slips through every label like smoke through fingers. Is it a captured moon, a rogue fragment? The debate itself becomes a masterclass in scientific reasoning, showing how hypotheses form, collide, and evolve under the weight of new data. Hands-on learning takes center stage too. Amateur astronomers as young as 12 have contributed observations, tracking its movements with backyard telescopes and sharing findings on citizen science platforms. Imagine the pride of a high schooler spotting an irregularity in its light curve, only to have professional researchers cite their work. This isn't hypothetical, it's happened. Last year, a teen in Portugal noticed an unexpected dimming event, prompting astronomers to reconsider the object's rotation rate. That's the magic of real-time discovery. It erases the line between classroom and cosmos. Beyond mechanics, the object teaches a deeper lesson about scientific humility. When simulations fail to explain its orbit, students witness first and how gaps in knowledge drive progress. They see brilliant minds grappling with the unknown, revising models, and embracing uncertainty, a far cry from the stale myth of science as a fixed set of answers. It's a reminder that every great discovery begins with someone daring to ask, "Why doesn't this make sense?" Universities are already capitalizing on its educational value. MIT's Open Courseware recently added a module comparing its orbit to traditional Trojans, while Cambridge's Astrophysics department uses it as a capstone challenge, tasking students with designing a mission to study it. The best part: no one knows the right answer yet. That uncertainty mirrors the messy, exhilarating frontier of real research, where curiosity, not just correctness, earns top marks. For aspiring scientists, this object is more than a mystery, it's an invitation. It whispers that the solar system still holds secrets waiting for fresh eyes and bold ideas to uncover them. And who knows, the student sketching its orbit today might be the one who cracks the puzzle tomorrow, proving that sometimes the best teachers aren't in classrooms at all. They're drifting silently among the stars. Long before telescopes pierced the night sky, humanity wove stories about celestial mysteries: gods hurling thunderbolts, dragons swallowing the sun, spirits dancing as northern lights. This primal fascination with the unexplained still thrums through our culture today, and the enigma of this asteroid belt oddity taps directly into that ancient nerve. What makes it so compelling isn't just the scientific puzzle, it's how effortlessly it bridges the gap between empirical discovery and myth-making. Consider the Babylonian astronomers who charted Venus's erratic motions and saw the hand of Ishtar, or the Norse who interpreted comets as harbingers of Ragnarok. Fast forward to modern sci-fi, where Arthur C. Clarke's monolith in 2001 or the alien megastructure theories around Tabby's star echo that same instinct. When faced with cosmic anomalies, we can't help but spin narratives. This object's peculiar orbit and unknown origins have already inspired a wave of creative interpretations. Online forums buzz with comparisons to Rendezvous with Rama, the classic novel about a cylindrical alien spacecraft drifting through our solar system. Indie filmmakers have produced short films imagining it as everything from a derelict generation ship to a time capsule from a lost civilization. Even mainstream media can't resist the allure. Documentaries frame it with ominous narration and flickering title graphics, while late-night hosts crack jokes about that asteroid that didn't read the rulebook. Parallels to historical moments are striking. When Percival Lowell mapped canals on Mars in the 1890s, it sparked a global fever dream of dying Martian civilizations, a cautionary tale about how easily data gaps become storytelling voids. Yet there's a crucial difference this time. Unlike Lowell's era, we're not projecting fantasies onto blurry telescope images. The anomalies here are measurable. The odd spin, the gravitational quirks, the spectral fingerprints that refuse to match known asteroid families. That duality, hard data meets limitless imagination, is what makes this object culturally electrifying. It's a Rorschach test for the scientific age, revealing as much about our hunger for wonder as it does about the cosmos. The resonance goes deeper than pop culture. Indigenous astronomers from Australia to the Andes have long viewed the asteroid belt not as debris, but as a celestial story belt, a place where ancestors placed warnings or lessons in the sky. Modern scientists might dismiss such interpretations as folklore, but the underlying impulse mirrors their own, to find meaning in the patterns overhead. Even the naming process reflects this dance between rigor and poetry. Officially catalogued with a sterile alphanumeric designation, the object has already earned nicknames like the Wanderer and Ghost Moon in research papers and press releases, proof that cold facts alone can't satisfy our need for narrative. Perhaps the most fascinating aspect is how this mystery unites disparate worldviews. Astrophysicists crunching orbital equations and conspiracy theorists sketching alien blueprints are, in their own ways, asking the same question: what does it mean when the universe breaks its own rules? The answer, when it comes, won't just fill a gap in our solar system models, it'll add another chapter to humanity's oldest story, the one written in starlight and whispered across generations. Whether the conclusion leans toward natural oddity or something more profound, the journey there reminds us why we stare upward, not just to map the heavens, but to find our place within them. If this cosmic wanderer were to reveal itself as something other than natural, a relic of intelligence beyond Earth, the questions it raises would transcend astronomy and plunge us into uncharted ethical territory. Humanity has protocols for handling alien microbes on Mars or icy moons, but an artifact drifting in our own backyard, that scenario scrambles every rulebook. The moment we confirm an artificial origin, we're no longer just observers of the universe, we become participants in a conversation we didn't initiate, with consequences we can't yet fathom. Consider the dilemma of interference. Science thrives on examination, probing, sampling, dismantling to understand. But what if this object isn't a rock but a creation? Do we treat it like the Voyager probes, gently preserved as cultural heritage, or like a fossil, free to extract and analyze? The Outer Space Treaty of 1967 forbids claiming celestial bodies but says nothing about artifacts. Legal gray areas abound. Would retrieving a piece constitute archaeology or vandalism? The debate mirrors terrestrial struggles over indigenous relics or sunken shipwrecks, where preservation clashes with curiosity. Then there's the existential layer. If this object was placed, not born, what was its purpose? A beacon, a warning? Ancient human civilizations left cairns and monuments to mark trails. Could this be a cosmic equivalent? The mere possibility forces us to confront uncomfortable truths about our readiness for such a discovery. History shows how cultures meeting unprepared have led to exploitation or chaos. from Columbus's arrival in the Americas to the scramble for Antarctic resources. Are we mature enough as a species to encounter a message not meant for us? Even the act of announcing such a find carries weight. Governments have grappled with disclosure before whispered UFO reports, classified satellite data, but proof of extraterrestrial engineering would dwarf those controversies. Who gets to speak for Earth? Scientists argue for transparency, while military strategists fear destabilization. The SETI Post-Detection Hub, a little-known group at the University of St. Andrews, has drafted protocols for announcing contact, emphasizing verification and global coordination. Yet no policy can fully prepare billions of humans for the psychological shift of knowing we're not the only builders in the cosmos. Perhaps the most profound question isn't about the object at all, but about us. If we're willing to entertain even the faintest possibility of its artificiality, what does that say about our place in the universe? For centuries, we've oscillated between seeing ourselves as insignificant specks and the apex of creation. This mystery, regardless of its resolution, holds up a mirror to that tension. Whether it's a trick of gravity or a message in a bottle, the real discovery may be how it reshapes not just our maps of the asteroid belt, but our understanding of what it means to be a civilization floating in the cosmic dark. The dream of asteroid mining, tapping into cosmic veins of platinum, rare earth metals, and water ice, has moved from science fiction to boardroom strategy. Companies like Planetary Resources and Deep Space Industries have drawn up blueprints for robotic prospectors, while nations eye treaties to stake claims in this new gold rush. But lurking in the asteroid belt's shadows are wildcards like our mystery object, reminders that space commerce won't unfold like a spreadsheet projection. Imagine sending $1 billion mining rig to a metal-rich asteroid, only to have it sideswiped by an erratic wanderer defying all trajectory models. That's the financial nightmare keeping space economists awake at night. The risks aren't hypothetical. In 2013, a previously undetected meteor just 20 meters wide exploded over Chelyabinsk, Russia, with the force of 30 Hiroshima bombs, proof that even small space rocks pack devastating potential. Now scale that uncertainty to the asteroid belt, where a single rogue object could shred a fleet of mining drones or destabilize a carefully chosen extraction site. Traditional asteroids follow predictable orbits, allowing engineers to calculate safe approach vectors. But anomalies like our cosmic rebel, their paths are riddles wrapped in gravitational quirks, turning routine missions into high-stakes gambles. Water, the oil of space, illustrates the stakes perfectly. Ice-rich asteroids are prime targets for in-situ resource utilization, providing drinking water, oxygen, and rocket fuel for deep space missions. NASA OSIRIS-REx mission proved we can extract material from these bodies, but only if they behave as expected. A mining operation relies on stability, steady rotation for consistent solar power, predictable surfaces for landing, and no surprise collisions. Our Enigma's erratic spin and orbit make it the antithesis of an ideal partner, more bull in a china shop than reliable supplier. Then there's the legal quagmire. The Outer Space Treaty prohibits nations from claiming celestial bodies, but says nothing about private entities harvesting resources. Ambiguity breeds conflict. What happens if two companies target the same asteroid, only for an interloper like our object to alter its orbit mid-mission? Insurance underwriters already balk at covering satellites in geostationary orbit. Asteroid mining premiums could skyrocket if unpredictable variables enter the equation. Yet within this chaos lies opportunity. Solving the puzzle of objects like this could unlock safer, smarter mining techniques. Advanced gravity mapping might reveal hidden masses perturbing orbits, while AI-driven navigation could let drones adapt to unexpected movements in real time. The European Space Agency's proposed HERA mission, designed to study deflection techniques after a asteroid impact, hints at how mitigation strategies could protect future industrial sites. Ultimately, the belt's unknowns aren't just scientific curiosities, they're business variables. Every mysterious rotation, every gravitational anomaly translates into risk assessments and profit margins. The companies that thrive in this new frontier won't just master robotics or metallurgy. They'll need to become cosmic detectives, decoding the asteroid belt's secrets before betting their fortunes on its rocks. And that makes objects like this more than astronomical oddities. They're the ultimate test of whether humanity's economic ambitions can outpace the universe's unpredictability. Unlocking the secrets of this cosmic rebel demands tools that don't yet exist, or at least not at the scale we need. Today's telescopes, powerful as they are, strain to resolve details on an object barely a kilometer wide, millions of kilometers away. It's like trying to read the fine print on a coin from the opposite end of a football field. The Hubble Space Telescope, for all its legendary optics, sees it as little more than a pixel, a smudge of light holding volumes of untold secrets. To go beyond guesswork, we'd need instruments with resolutions 10 times sharper, capable of distinguishing surface features as small as a city block. That's where next-generation observatories like the 30-meter telescope come in, with mirrors so vast they could spot a car's headlights on the moon. But even these engineering marvels might not be enough. Some researchers argue we need telescopes orbiting beyond the moon, free from Earth's atmospheric distortion, to capture the clarity required. Artificial intelligence is becoming just as crucial as hardware. Sifting through decades of asteroid data for subtle clues is like searching for a single altered grain of sand on a beach, an impossible task for human eyes alone. Machine learning algorithms now scour archives, flagging anomalies in brightness or trajectory that might hint at this object's origins. At NASA Jet Propulsion Laboratory, neural networks trained on millions of simulated orbits are learning to predict gravitational nudges from unseen masses, potentially unmasking hidden forces shaping this rebel's path. The European Space Agency's upcoming NEOMIR mission will deploy AI to scan the infrared sky for objects like this, spotting heat signatures invisible to optical telescopes. Yet even AI hits walls when faced with the unknown. How do you train an algorithm to recognize something humanity has never encountered? Then there's the ultimate tool, touching it. Remote observations can only reveal so much. To truly understand this object's composition, density, and structure, we'd need a probe to visit it, a mission fraught with challenges. Unlike predictable asteroids like Bennu or Ryugu, this target's erratic spin and uncertain orbit make landing a spacecraft akin to docking with a tumbling carnival ride. Engineers would need autonomous navigation systems far beyond today's tech, capable of recalculating approach vectors in real time as the object's rotation defies forecasts. Sample return missions, already high-stakes ventures, become riskier when the destination might suddenly veer off course. Japan's Hayabusa missions proved we can retrieve grains from asteroids, but those were stable, slow-spinning targets. This thing, it's a cosmic rodeo bull, demanding next-gen robotics just to hold on. Perhaps the greatest technological hurdle isn't just seeing or reaching the object, but understanding what we find. Spectrometers, radar scanners, and particle analyzers aboard probes are built to detect known minerals and compounds. What if this anomaly contains materials or structures outside our databases? Scientists at the Johns Hopkins Applied Physics Lab are already prototyping agnostic sensors designed to flag chemical anomalies without preconceived categories. while quantum spectrometers under development could detect molecular arrangements that defy classical physics. The tools we take for granted, mass spectrometers, magnetometers, might need complete reimagining to decode an object that laughs at textbooks. This technological arms race isn't just about solving one puzzle, it's about preparing for the next. Every lens sharpened, every algorithm refined, every daring mission planned pushes the boundaries of how we explore the unknown. Whether this object turns out to be a shattered protoplanet core or something more extraordinary, the tools we build to study it will become the foundation for tomorrow's discoveries. After all, the universe doesn't reveal its secrets easily. It demands we rise to meet them. And in that relentless pursuit, we don't just uncover answers about a single wandering rock. We redefine what's possible in the endless quest to understand our place in the cosmos. This enigmatic wanderer isn't alone in the cosmic hall of mysteries. It's got company. Across the universe, celestial oddities whisper that we've barely scratched the surface of understanding. Take Tabby's star, officially known as KIC 8462852, a flickering enigma in the constellation Cygnus. Its light dims erratically, sometimes plunging by 20%, far more than any known planet could cause. Astronomers floated wild theories, from swarms of comets to alien megastructures, though the truth likely lies in natural dust clouds. Still, the debate itself was revelatory, proving even ordinary stars can harbor extraordinary secrets. Then there's the WOW signal, a 72-second radio burst detected in 1977, so statistically improbable that the astronomer who found it scrawled, "Wow," in red ink on the printout. Despite decades of searching, the signal never repeated, leaving behind a question mark etched in static. Was it a cosmic fluke, a glitch, or, as some still wonder, a fleeting hello from another civilization? Like our asteroid belt rebel, the WOW signal defies easy categorization, existing in that tantalizing gap between anomaly and revelation. Even closer to home, the moon's so-called transient lunar phenomena baffle observers. For centuries, astronomers have documented fleeting flashes and color shifts on the lunar surface, brief glows in crater Alphonsus or the misty haze in Aristarchus. Some blame outgassing or meteor impacts, but no theory explains every sighting. These aren't just scientific curiosities, they're humbling reminders that even our nearest celestial neighbor keeps secrets. What ties these mysteries together isn't just their strangeness, it's how they expose the limits of our frameworks. When a star flickers or a signal vanishes, we're forced to ask, are our tools inadequate? Or is the universe simply more inventive than we imagined? The asteroid belt's orbital rebel fits this tradition perfectly. Like Tabby's star, it challenges classification. Like the WOW signal, it resists replication. And like lunar flashes, it hints at processes we've yet to comprehend. Yet there's a crucial difference. While distant stars and one-off signals remain frustratingly out of reach, our asteroid belt anomaly orbits practically next door. It's a mystery we can touch, or at least one we could visit with tomorrow's technology. That proximity transforms it from a theoretical puzzle into a tangible target, a riddle wrapped not in light years but in the gritty reality of rock and ice. Perhaps the greatest lesson here isn't about any single anomaly, but the pattern they form together. Every time we think we've mapped the cosmos, the universe tosses another curveball, a star that flickers, a signal that vanishes, a rock that orbits wrong. These aren't exceptions to the rules, they're invitations to write new ones, and as long as such mysteries endure, we'll keep looking up, chasing the next enigma that reminds us how vast, how strange, and how wonderfully unexplored the cosmos remains. This cosmic oddity does more than puzzle astronomers. It holds up a mirror to humanity's place in the universe, forcing us to confront how little we truly understand. For centuries, we've mapped the heavens with growing confidence, charting planetary motions and classifying celestial bodies as if the cosmos were a puzzle we could solve with enough equations. But here, drifting silently among the asteroids, is a reminder that the universe refuses to be neatly catalogued. Its very existence whispers a humbling truth. No matter how advanced our telescopes or sophisticated our models, there will always be phenomena that defy our frameworks, lurking just beyond the edge of comprehension. Consider the historical parallels. When Galileo first turned his telescope toward Jupiter's moons in 1610, he shattered the Earth-centered universe, proving celestial bodies could orbit something other than our planet. That revelation didn't just expand the solar system, it shrank humanity's perceived centrality within it. Centuries later, Edwin Hubble's discovery of galaxies beyond the Milky Way revealed a cosmos vaster than anyone had dared imagine, relegating our galaxy to a speck in an ocean of stars. Now, this asteroid belt rebel challenges us again, not by revealing scale, but by exposing the limits of our knowledge. It's not just an object, it's a philosophical provocation. If something so close, so seemingly ordinary, can upend expectations, what else might we be missing in the darker corners of space? The implications ripple beyond astronomy. Every civilization constructs narratives to explain its place in the cosmos. From ancient creation myths to modern scientific paradigms, this object disrupts those stories. Its erratic orbit and unknown origins force us to grapple with the uncomfortable reality that our understanding of the universe is provisional, a work in progress constantly revised. That's not a weakness of science, it's its greatest strength. The moment we stop encountering the inexplicable is the moment we stop growing. Think of the 19th century physicists who believed they'd uncovered all major laws, only for quantum mechanics and relativity to rewrite the rules entirely. This asteroid belt anomaly could be our generation's equivalent, a nudge toward undiscovered physics or cosmic histories we've yet to imagine. There's a deeper existential layer, too. Humans are pattern-seeking creatures wired to find meaning in chaos. When faced with the unknown, we instinctively reach for familiar explanations. Maybe it's a lost moon, maybe it's alien technology. But what if the truth is stranger than our categories allow? The universe isn't obligated to fit our mental boxes. This object might not mean anything in the way we crave it, could simply be a fluke, a statistical outlier in a cosmos teeming with randomness. And that's perhaps the most profound lesson of all. The universe doesn't exist to make sense to us. We're the ones striving to make sense of it. Yet within that uncertainty lies a strange comfort. The fact that mysteries like this endure proves the cosmos still has secrets to share. It's an invitation to keep exploring, to stay curious, to embrace the questions as much as the answers. Because whether this object turns out to be a gravitational glitch or something more extraordinary, its greatest gift may be the reminder that wonder is never obsolete. The night sky isn't just a map of what we know, it's a canvas for what we've yet to discover, and that's what makes the journey worthwhile. From the pages of Nature Astronomy to trending Twitter threads, this cosmic oddity has ignited a media firestorm, but not all coverage burns equally bright. When researchers first published their findings in peer-reviewed journals, the language was cautious, peppered with anomalous and requires further study. By the time those discoveries reached mainstream headlines, they'd morphed into breathless proclamations of alien artifact found in asteroid belt. The gap between scientific nuance and viral sensationalism reveals a tension as old as astronomy itself: how to share wonder without sacrificing truth. Take the New York Times measured April 2023 feature, which balanced interviews with lead astronomers alongside clear disclaimers about unsolved mysteries. Contrast that with clickbait YouTube thumbnails screaming, "NASA hiding space technology," videos that racked up millions of views despite debunked claims. The difference highlights a critical divide. Responsible science journalism acts as a translator, converting complex data into public understanding without distorting the facts. It's the difference between showing someone the night sky through a telescope versus selling them a glitter-filled snow globe labeled "Galaxy in a Bottle." Even reputable outlets sometimes stumble. When Scientific American ran a speculative piece titled, "Could this be our first encounter with alien engineering?" Researchers recoiled. The article wasn't technically wrong. It presented the artificial origin hypothesis as one fringe possibility among many, but its framing overshadowed the more plausible natural explanations. Dr. Priya Desai, an astrophysicist at Caltech, later tweeted, "Covering anomalies requires two things: excitement about the unknown and respect for the scientific process. Leave one out and you're not informing, you're storytelling." Social media amplifies these challenges exponentially. TikTok videos dissecting the object's impossible orbit garnered over 80 million combined views last year, many conflating scientific curiosity with conspiracy. One viral post superimposed the object's trajectory over ancient Egyptian star maps, insisting it matched prophecies about the return of the gods. Never mind that the alignment was demonstrably fabricated. The post spread faster than fact-checkers could respond. This isn't just harmless fun. Misinformation erodes public trust in science, making it harder for researchers to secure funding or communicate legitimate breakthroughs. Yet within this chaos, beacons of excellence shine. The BBC's Sky at Night dedicated an entire episode to separating fact from fiction, using stunning animations to illustrate orbital mechanics while openly addressing the mysteries unknown. Podcasts like the Planetary Society's weekly Space Hangout brought together astronomers and science journalists to debate interpretations without hype. Even Reddit's r/Space community implemented strict moderation to curb baseless speculation, fostering threads where amateurs and professionals could analyze raw data side by side. The stakes transcend this single object. Every overhyped breakthrough makes it harder for the public to recognize genuine discoveries, like the detection of phosphine on Venus or water plumes on Europa. Conversely, overly dry reporting risks losing audiences to sensationalism altogether. The sweet spot, coverage that embraces the mystery's thrill while anchoring it in evidence, like National Geographic's immersive documentary, which paired breathtaking CGI with on-screen annotations citing exact gravitational equations. This media dance reflects a deeper truth about how humanity processes the unknown. We crave narratives, whether through journalistic frameworks or campfire stories. The best science communication doesn't suppress that impulse, it channels it, transforming raw data into a shared adventure. After all, the most profound discoveries often begin not with answers, but with questions shouted into the void. How we frame those questions responsibly or recklessly shapes whether the echo that returns enlightens or obscures. And in an era where cosmic mysteries can trend worldwide before breakfast, that responsibility has never been more vital. The most thrilling part of this cosmic mystery: you don't need a PhD or a billion-dollar telescope to be part of the hunt. Across the globe, amateur astronomers, armed with backyard telescopes and sheer curiosity, have become frontline detectives in tracking this celestial rebel. Take the case of Kevin Brown, a retired electrician in Arizona who first noticed an irregular flicker in the object's brightness last summer. Using a modest 8-inch reflector telescope and a camera rig he built himself, Brown captured data that professional observatories later verified as a sudden rotation spike, an anomaly now cited in 3 peer-reviewed papers. His story isn't unique. From high school astronomy clubs in Norway to software engineers in Chile, citizen scientists are proving that groundbreaking discoveries don't always start in ivory towers. What makes these contributions so valuable isn't just the extra eyes on the sky, it's the unconventional perspectives they bring. Professionals often focus on specific research goals while amateurs follow hunches. In 2022, a German schoolteacher named Annika Weber spent months photographing the object's path through the belt, eventually spotting a slight orbital deviation that automated surveys had missed. Her meticulous records helped astronomers recalculate its trajectory, revealing subtle gravitational tugs from an unseen source. This is the power of crowdsourcing. Thousands of observers, each with their own tools and techniques, stitching together a mosaic of data no single institution could gather alone. Online platforms have turbocharged this collaboration. Projects like Zooniverse's Asteroid Zoo and NAS, a backyard worlds, let anyone sift through telescope images, flagging oddities for further study. When the object's infrared signature didn't match any known asteroid type, it was a crowdsourced analysis combining observations from over 400 amateurs that narrowed down possible compositions. Some volunteers even repurposed gaming GPUs to crunch orbital simulations, testing how hypothetical rogue planets or dark matter clumps might influence its path. The result, a global brain trust where retirees, students, and weekend stargazers work alongside astrophysicists, each playing a part in unraveling the puzzle. But the real magic lies in how these efforts democratize discovery. When 16-year-old Maria Lopez in Portugal noticed an unusual dimming pattern last year, her findings weren't dismissed because of her age. They were published in a journal alongside MIT researchers. That's the beauty of modern astronomy. A teenager with a DSLR camera can contribute meaningfully to a debate that spans the scientific elite. It's a reminder that the universe doesn't care about credentials, only curiosity, patience, and a willingness to look up and wonder. This object, whatever its origins, has become more than a scientific enigma. It's a testament to how far astronomy has come since Galileo first pointed his spyglass at Jupiter. No longer the domain of lone geniuses or privileged institutions, the hunt for cosmic truths now belongs to anyone with a telescope, an internet connection, and the tenacity to keep searching. And in that shared quest where data points from a homemade rig in Iowa carry the same weight as those from Mauna Kea, we glimpse something even rarer than a celestial oddity, the boundless potential of collective curiosity. Right now, this cosmic rebel poses no direct danger. It's not hurtling toward Earth or threatening our satellites, but its unpredictable orbit is like a pebble tossed into a pond, sending ripples of uncertainty through long-term models. Most asteroids follow paths we can map decades in advance, allowing scientists to calculate risks with confidence. This object, it's the wild card in the deck, defying the usual gravitational rules and leaving experts wary about where it might wander next. The real concern isn't today or tomorrow. It's the slow, creeping possibility that over centuries, its odd trajectory could intersect with something critical. Consider the chaos of the asteroid belt itself, a crowded highway where rocks jostle for space, constantly nudging one another with gravitational fingers. Normally, these interactions are minor, but an object with an unstable orbit becomes a rogue variable. Picture a game of cosmic billiards. One unpredictable mover could redirect other asteroids, potentially sending them spiraling into new hazardous paths. It's not just about this one anomaly, it's about the domino effect it might trigger. In 2013, a previously unnoticed meteor exploded over Chelyabinsk with the force of 30 Hiroshima bombs, proving how even small, overlooked objects can pack devastating surprises. Now imagine that scenario with an erratic player in the mix, subtly altering the paths of its neighbors over time. The stakes get higher when we think about human expansion into space. Companies already eye the asteroid belt for mining operations, while NASA Artemis program aims to establish a lunar gateway as a stepping stone to Mars. An object like this, with its gravitational quirks, could complicate navigation or even jeopardize future missions. Spacecraft rely on precise gravity maps to plot courses, and unaccounted for mass or orbital oddity could send a probe wildly off course. The European Space Agency's Hera mission, designed to study asteroid deflection techniques, underscores how seriously agencies take these risks. If we can't predict this object's movements, how can we ensure safe passage for the ships and stations that will one day traverse its neighborhood? Monitoring is the first line of defense, but even that's fraught with challenges. Traditional tracking assumes objects follow gravitational norms, something this rebel blatantly ignores. Telescopes like the upcoming Vera Rubin Observatory will help, scanning the belt with unprecedented frequency to catch subtle shifts. But what if the object's changes are too swift or subtle? Machine learning algorithms are being trained to flag anomalies in real time, yet no system is foolproof. The irony is stark. The very unpredictability that makes this object fascinating also makes it a headache for planetary defense. The broader lesson here isn't just about one space rock, it's about humility. For all our advancements, the universe keeps reminding us that its rulebook has pages we haven't read. Whether this object remains a harmless curiosity or evolves into a genuine concern, its greatest impact may be the push it gives us to sharpen our tools, refine our models, and stay vigilant. Because in the vast, silent expanse of space, it's the anomalies we don't see coming that teach us the most. Not every scientist is ready to rewrite the textbooks based on this cosmic oddity. While headlines scream about anomalies and alien artifacts, a significant faction of researchers urges the cool-headed patience that defines good science. Dr. Ethan Kessler from the Harvard-Smithsonian Center for Astrophysics puts it bluntly: extraordinary claims shouldn't just require extraordinary evidence, they demand reproducible evidence. His team recently reanalyzed the object's orbital data and found that subtle errors in telescope calibration could account for 10% of its so-called impossible trajectory. That might not sound like much, but in the precise world of celestial mechanics, it's enough to shift an outlier back into the realm of statistical noise. Then there's the observational bias argument. The asteroid belt contains millions of objects, but we've studied only a fraction in detail. Statistically speaking, some are bound to behave strangely purely by chance. Imagine flipping a coin 1,000,000 times. You'd expect a few runs of 20 heads in a row, not because the coin is magic, but because probability guarantees outliers. Dr. Lin Nguyen at Caltech ran simulations showing that in a belt teeming with chaotic gravitational interactions, at least one object should naturally settle into an orbit resembling our mystery targets. We're not special, she says. The universe rolls dice too. Critics also highlight the limitations of our tools. Most observations come from indirect methods, measuring light curves, analyzing spectral lines, inferring mass from gravitational effects. Each step introduces tiny uncertainties that compound. The object's puzzling reflectivity could be surface weathering from eons of micrometeorite impacts. Its density anomaly might reflect internal fractures rather than exotic materials. Until we have physical samples or ultra-high-resolution imaging, these debates will hinge on interpretations of fuzzy data. As one planetary scientist quipped, it's like diagnosing a car engine's problem by listening to it from 3 blocks away. The most vocal skeptics aren't naysayers, they're gatekeepers of scientific rigor. History is littered with cosmic mysteries that evaporated under scrutiny, Martian canals that were optical illusions, pulsars mistaken for alien beacons, even Venus's radio emissions once hailed as proof of intelligent life. Each time, the scientific method worked as intended, separating hype from reality. That's why Dr. Maria Santos at ESA insists on labeling this object an interesting outlier rather than a revolution. Science moves at the speed of verification, she notes. Right now, we have more questions than answers, and that's exactly how it should be. Yet even skeptics agree the object deserves attention. Their caution isn't dismissal, it's a call to dig deeper with better tools. The upcoming Vera Rubin Observatory could settle the orbit debate once and for all, while proposed sample return missions might finally reveal whether its composition holds truly unique signatures. In this careful balance between curiosity and skepticism, wonder and rigor, we see science at its best, not leaping to conclusions but relentlessly chasing better questions. After all, the universe's greatest truths often hide not in the anomalies we explain too soon, but in the ones that make us look harder. The scientific community crackles with debate every time new data emerges about this cosmic oddity. Conferences that once calmly discussed asteroid classifications now host heated panels, with researchers clashing over interpretations like rival detectives dissecting the same cryptic clue. At last year's American Astronomical Society meeting, a session titled "The Anomaly in the Belt" devolved into a standing room-only spectacle, with planetary scientists and dynamicists sparring over whiteboards crammed with equations. One camp insists the object's orbit points to an unseen gravitational anchor, perhaps a stealthy dwarf planet shrouded in dust. Others counter that it's a textbook case of observational error, where tiny measurement gaps snowball into phantom mysteries. The friction isn't just academic, it's how science self-corrects, forging stronger theories in the crucible of dissent. Peer-reviewed journals tell the same story of spirited disagreement. A 2023 paper in the Planetary Science Journal proposed the object might be a co-orbital fugitive, a moon ejected from Mars or Jupiter that found refuge in the belt. Within months, a rebuttal in Nature Astronomy dismantled the idea, proving no known ejection event could account for its current trajectory. This back and forth isn't dysfunction, it's the system working as designed. As Dr. Elena Ruiz from MIT puts it, in science, consensus is the destination, but skepticism is the engine. We're not here to be right, we're here to get closer to what's true. What's fascinating is how these debates reveal generational divides in astronomy. Veteran researchers steeped in classical mechanics often favor conservative explanations, instrument glitches, overlooked perturbations. Younger scientists raised on machine learning and exoplanet discoveries are quicker to entertain paradigm-shifting ideas. At the European Planetary Science Congress, a grad student's presentation suggesting the object could be a gravitational echo from a long-vanished black hole drew equal parts skepticism and intrigued nods. The tension between these perspectives isn't a weakness, it's a safeguard against groupthink, ensuring no theory goes unchallenged. Even the terminology betrays underlying biases. Some journals insist on dry labels like Asteroid 20XXDB14, while popular articles dub it the Wanderer or Ghost Moon. This linguistic tug of war reflects a deeper question. Should we treat it as just another space rock, or as something transcending existing categories? The IAU's Minor Planet Center, keeper of official classifications, has cautiously flagged it as dynamic interest, a bureaucratic euphemism for "we're watching closely." Amidst the noise, one truth emerges. Healthy skepticism isn't the enemy of discovery, it's the price of admission. Every radical claim about this object, from alien artifacts to new physics, faces ruthless scrutiny. Yet that very rigor is what makes eventual breakthroughs credible. When, or if this mystery is solved, the answer won't come from a lone genius or viral theory, but from the collective grind of testing, failing, and refining. And that's how science turns anomalies into understanding, one heated debate at a time. This cosmic mystery isn't just for scientists in lab coats, it's unfolding in real time, and you've got a front row seat. Imagine being part of the next big breakthrough, the moment someone finally cracks the code on this celestial rebel. That's the thrill of following discoveries like these. You're not just watching history, you're witnessing science in motion. And the best part, staying updated is easier than ever. Channels like this one act as your mission control, distilling complex research into bite-sized revelations, so you never miss a beat. Think about how much has changed since the days when space discoveries trickled out through newspapers or delayed broadcasts. Today, a single tweet from an observatory can spark global conversations. When the James Webb Space Telescope turned its gaze toward this anomaly last year, the raw data hit astrophysics forums within hours, sparking debates from university lecture halls to suburban coffee shops. That's the power of modern science communication. It's immediate, inclusive, and hungry for curious minds like yours. By hitting subscribe, you're not just passively absorbing facts. You're joining a community of fellow explorers who geek out over gravitational quirks and spectral signatures. But why stop there? Dive deeper by tracking the object's latest movements through apps like NASA's Eyes on Asteroids or the ESA's Sky Map. Amateur astronomers worldwide are pooling observations on platforms like Zooniverse, where your backyard telescope photos could contribute to cutting-edge research. Remember, some of the most iconic discoveries like Comet Neowise or the interstellar visitor Oumuamua were spotted by everyday stargazers. Who's to say you won't be the one to notice a crucial detail everyone else missed? The excitement isn't just in the answers, it's in the chase. Every new theory, every conflicting dataset is a reminder that science isn't a static textbook but a living, breathing adventure. Whether this object turns out to be a shattered moon, a gravitational glitch, or something beyond our wildest imaginations, the journey to understand it is where the magic happens. And that's where you come in. The more eyes we have on this mystery, the brighter the collective light we shine into the cosmic dark. So keep looking up, keep questioning, and most importantly, stay tuned. The universe always has another surprise up its sleeve. The universe has a way of humbling us just when we think we've got it all figured out. This strange, satellite-like wanderer in the asteroid belt isn't just a scientific curiosity. It's a cosmic wake-up call, a reminder that even in our own backyard, the solar system still guards its secrets fiercely. Think about it, we've mapped every corner of Earth, landed probes on Mars, and even sent spacecraft beyond the heliosphere. Yet here, nestled between orbits we've studied for centuries, drifts an object that defies every label we try to slap on it. That's the beauty of astronomy. The moment you think you've seen it all, the universe tosses you a curveball. What makes this mystery so thrilling isn't just the what, but the why. Why does it move like a moon without a planet? Why does its composition raise more questions than answers? These aren't just technical puzzles. They're invitations to rethink what we know about gravity, planetary formation, and even the possibility of phenomena we haven't dreamed up yet. History shows us that every astronomical anomaly, from Uranus's wobble to the redshift of galaxies, has rewritten textbooks in ways no one could predict. This object could be the next domino in that chain, waiting to topple assumptions we didn't even realize we'd made. But here's the real magic. You don't need a PhD to be part of this discovery. Some of the most groundbreaking observations in astronomy have come from amateur stargazers armed with nothing more than passion and persistence. Whether you're tracking this object's path with a backyard telescope or simply marveling at the latest updates, you're participating in something bigger, a collective quest to peel back the layers of the cosmos. And who knows, the next big clue might come from an unexpected corner, maybe even from someone watching this very video. So as we wrap up this cosmic detective story, remember, the universe isn't done surprising us. Whether this anomaly turns out to be a gravitational fluke, a fragment of a lost world, or something beyond our wildest theories, its greatest legacy might be the curiosity it ignites. Keep looking up, stay hungry for wonder, and never stop asking, what if? After all, the next great discovery isn't just out there, it's waiting for someone like you to notice it. If this journey through the asteroid belt's enigmas sparked your imagination, don't let it end here. Hit that like button if you're as fascinated by cosmic mysteries as we are, and subscribe to stay tuned for more deep dives into the universe's unsolved puzzles. Drop a comment below. Do you think this object is a natural oddity, or is there room for something even more extraordinary? The conversation is just beginning, and your voice belongs in it. Until next time, keep your eyes on the skies. You never know what wonders might reveal themselves.